By now, the whole world knows about OpenAI Sora. They had also given a technical report alongside their press release, but it doesn't have as many details. And we have seen in the past few days that OpenAI has been very hush-hush in terms of releasing what dataset they have used and what are the training techniques that they have used to build Sora.
What data was used to train Sora?
We used publicly available data and licensed data.
So videos on YouTube?
I'm actually not sure about that.
Okay. What about Shutterstock?
I'm just not going to go into the details of the data that was used.
Fortunately, researchers at Lehigh University along with Microsoft released a reverse engineering paper where they talk about how Sora might have been developed. In this video, I'm going to explain you the details that they have shared in this technical report. So let's jump in.
Sora.
So as you can see, this has been released by Microsoft Research, and there is only one researcher who is from Microsoft, but they have worked in collaboration with Lehigh University authors to publish this paper, which is a background review of technology limitations and opportunities of large vision models. Like I said, this is not an official report from OpenAI. This is just a reverse engineering paper that they have produced looking at the old research along with the technical report that OpenAI has given at a very high level. And that is what they mention over here as well. They introduce what Sora is, and they mention that compared to previous models, it is distinguishable because of the 1 minute long high quality videos that Sora is able to generate. And the way it works is given a instruction prompt such as a text or a text with some image or a video itself. OpenAI Sora is able to generate the text or animate the image or convert that video into a different format. What the authors claim is that Sora is a pre-trained diffusion transformer model which employs a space-time latent patches as its building block. These patches are analogous to word tokens in large language models and provide Sora with details of visual phrases to be used to construct the videos. Sora's text-to-video generation is performed by a diffusion transformer model starting with a frame filled with noise, which is iteratively then denoised to generate a high-quality video. So what do they mean by this? Let's dive deeper. This is what their architecture proposal is for Sora, how they might be using, and we will dive deep into each of these components. But at a high level, what they say is that Sora uses a clip model along with the GPT-v4 model to take in the video and the text prompt from a human and embed it into the diffusion transformer model. Along with this, they have an encoder and decoder which takes in the noised input and then gives out the high quality video output. So we'll look at each of these components in detail and let's read through the paper. What they're talking about in the introduction is things like vision transformers and diffusion models. So I will just give you a brief of what are vision transformer models and diffusion models. So in a large language model for a text-based system, what we have is a model which is your large language model, and it takes in the input which will be hi, my name is ... and it takes in these inputs and it is then supposed to generate some output where it will say something like chat GPT. And this way it is able to generate tokens one after another, which is the vocabulary is text tokens. In case of vision transformers, the difference is that instead of these text inputs, it takes in the patches of images as input, which are the pixels. So imagine that you have an image of a cat, and let me try to draw a cat over here. Vision transformer model do is they convert this image into smaller patches, and all of these patches are then fed into the transformer model, which is VIT in this case, and vision transformer model then takes in these patches of images and tries to do a classification task or a separate generation tasks on top of it. So this is about transformers model with images as input. What are diffusion models? So diffusion models have got quite popular in the past few years, with some of the popular ones as Stable Diffusion and Midjourney. The idea behind diffusion models is imagine that you have an image of a cat, and this image has some bit of noise inside it. And what you want is that you want to pass it through a diffusion model which predicts what are the different elements of noises present inside this image. So it might predict something like this. And what happens is once you take in the original image and subtract the noise from the image, you actually get a good quality, cleaner image of a cat. And this is the whole high-level concept behind diffusion models. So what happens is that the model does not do it in a single timestamp where it predicts the complete noise of the image at once. Instead, it does it repetitively, wherein first it identifies some bit of noise, and once you subtract it, you still get an image but with slight noise inside it, and you feed in this image into the model and try to repeat it again to identify a new set of noise in the image, and then again try to clean it up. So iteratively, when you do it hundreds of times inside the image, you get a much cleaner image and a very high definition output. So this is the idea behind diffusion models. So this is what they mention over here, that diffusion models offer a mathematically sound framework for converting noise into images with units. What they also claim is that Sora might be using clip model as a function of an image encoder. So clip model is specialized into identifying text and image correlations. How it was trained is that it has a text encoder and an image encoder. The image is fed into the image encoder and the text is fed into the text encoder. And the embeddings that come out of these are then tried to match together for similar looking text and images, and are tried to keep very far apart for different image corresponding to a different text. This way the model learns to identify similarities between the similar looking images and text and gives high quality embeddings for those. So what they mention as the architecture of Sora is that Sora is a diffusion transform models which has three parts. A time-space compressor first maps the original video into latent space. A VIT then processes the tokenized latent space representation and outputs the denoise latent representation, and a clip-like conditioning mechanism to basically augment the text with the images and videos. So what you do to train a diffusion transform model is that you take an original video, add some noise into it, and then you pass it into the diffusion transformer model, the noise latent space, and ask it to generate the cleaner latent space out of it. So this is what they are shown over here, that they take a clean video, they add some noise to it, and then from there they feed the noise latent space into the diffusion transformer block, and through the denoise latent space we pass it through the decoder to get the cleaned up video again. For text, video and image augmentation, what they show is that they are using some humans using GPT-4 to augment using clip for images and text together, which also goes into your diffusion transformer block as a feature to augment the video according to the human instruction. So let's dive deep into each of these components. What the technical report of OpenAI says is that they are able to support variable resolutions and aspect ratios. This means that they can support anything between 1920 x 1080 pixels to 1080 x 1920 pixels. Due to this variable aspect ratio training, they are able to generate much more high quality and better videos. What they claim in their technical report is that training on videos that are cropped into square leads to an unnatural composition and framing, whereas training in the native sizes improves the framing. What their technical report also talks about is how they unify the visual representations. What they simply mention in their technical report is that Sora turns videos into patches by first compressing it into lower dimensional latent space. So the authors of this report then try to reverse engineer it and mention some of the techniques using which a video can be compressed into these patches and latent space. The first technique that they mention is spatial patch compression, which involves transforming the video frames into fixed size patches, similar to the method applied in VIT. And this approach is particularly effective because it is able to accommodate varying resolution and aspect ratios. So what they mention, as I had discussed before, is that they crop the original image into different image patches, and then these image patches are flattened out and then fed into the model. But a video is not a single frame. It has multiple image frames inside it which spread across the timeline. And for that they talk about spatial temporal patch compression, in which they use 3D convolution networks and try to apply filters across the time domain as well. So they still go about performing patching of different video frames, but then also apply the filter across the time domain into the filter. These patches are then flattened out and fed into the model. What they mention is that a large patch size and kernel size is used for efficient compression, and here we expect a fixed patch size for simplicity, scalability, and training stability. Now videos could be very long and very small as well, and so to fit it into a single batch size could be a difficult task. For this, a very well-known technique is patch and pack. What happens in this case is that you have different variation sizes of images and you try to do a patchify or generating patches out of it. And then what you do is you drop certain patches from each of these images to maintain the aspect ratio, and then flatten out these along with some padding to basically have a single batch out of it. This, the paper mentions, can be assumed as a data augmentation in which we are adding some kind of noise and we want to generate the actual output video out of it. However, what they mention is that the 3D consistency of Sora is superb, and thus they believe that OpenAI is likely to use a super long context window for Sora instead of dropping any of these patches, which could also make it very computationally expensive. What they conclude from this discussion is that Sora first compresses visual patches into low-dimensional latent representations and then arranges these latent patches along with the noise before feeding it to the diffusion transformer model. This is the representation of a VIT model in which the patch of images are sent into the transformer model, and from this model you are able to then generate the predicted noise, which is then subtracted from the image or the video to generate higher quality images. Since Sora is able to generate high-resolution videos, what they mention is that Sora might be using a cascaded way of upsampling the videos generated, which can be seen even from their technical report, in which they mention about as the compute increases, the quality of their video also increases. What the authors of this paper mention is that Sora might be leveraging cascaded diffusion model architecture, which is composed of base, model, and many space-time refiner models, which is depicted in this diagram, in which case you have an input text prompt along with the base model, and then this base model is upsampled into higher and higher resolutions until you get the required resolution. This way you are able to iteratively improve upon the video quality while still maintaining the coherence and the video quality output. What they mention is on the latent encoder part, most of the research is done on pre-trained stable diffusion models, but instead they think that Sora might be able to train their own VAE encoder from scratch on video data for better quality latent space. Now they discuss about how Sora is able to capture language instructions and generate videos around it. They first discuss about the text-to-image models that are pre-existing, and one of the methods that OpenAI used to train DALL-E 3 was to use a captionator inside DALL-E 3 to have better captions for the image. What they mention is that the poor quality of data particularly prevails because of the noisy data and short captions that omit a large amount of visual information. The caption improvement approach addresses this issue by recaptioning the images with detailed descriptive captions. So what they mean by this is that, for example, let's say the user is saying that draw me a cat, and because they are saying just this much, maybe the model will generate something like this with just the face of the cat inside the image. But ideally what they wanted is a cat with a very zoomed in face in the image, not the body part. And so what the image captioning model does is that when it sees an image of, let's say, just the cat face together, it gives out a caption saying a close-up of a cat smiling. This way you get much more better captions for the model to be trained on top of, and you use this caption in DALL-E 3 and try to generate this image back. However, what they mention is that these methods introduce a potential issue of mismatch between the actual user prompt and the descriptive image captions. To address this, what they do is they use a LLM to rewrite the short user prompt into a detailed lengthy instruction using the caption that was generated. So what they do is, once they have the captions generated by the captionator, they use the original user query. Along with this, they feed it to an LLM model, let's say in this case GPT-4, and it gives you a query which adds both the description of the user along with the caption to generate a much better query. So in this case, the LLM might generate draw me a close-up of a smiling cat. And so then this input is fed into the DALL-E 3 model, which gives this image output to make it more coherent to human instruction. And so what they say is this ensures that the model text input received in inference time are consistent with those in the model training. What they mention is that Sora might also be using a similar approach but for text to video instead of text to images, in which case they might be using GPT-4v model for taking in the video captionator along with the user query to rephrase it into a better quality query. What they mention is that the process of collecting the data for training such a caption is unknown and likely labor intensive, as it may require detailed description of the videos. And they mention that how to improve the video caption warrants further investigation, and it is critical to enhance the instruction following ability of the text-to-video model. On the prompt engineering aspect of how different components interact based on images and text, they didn't give much details into this paper, but just at a high level gave a brief description about each of those components. What they also mention in the paper is that OpenAI uses a detection classifier which understands that which are the videos generated by Sora, as well as a text classifier is deployed which understands potentially harmful text that is inputted into Sora that it can be discarded. Some of the limitations that are mentioned both in the technical report and in this paper are the challenges in the physical realism. For instance, consuming a portion of cookie might not result in corresponding bite mark. As you can see in the technical report by OpenAI, what they show is a man eating a burger and its bite mark is actually shown inside the video. And similarly, when the painter is drawing a painting, wherever the brush strokes are made, the color is only put up into those places. But if you will notice closely, what you will see is that the brush strokes are being made at different places, whereas the actual paint is coming in other places where the brush is not present at the moment as well, which is basically far from the realism. Another video is shown of a glass which defies gravity and breaks it apart. This paper gave us a sneak peek inside how Sora might be developed, and this will actually help in developing open source solutions similar to Sora, which have Sora-like capabilities in video generation. If you liked the content that I shared today, make sure to like and share this video. Also, don't forget to subscribe, as I will be putting up more such content in the upcoming weeks. Until next time, this is Anubhav Shrimal. Bye-bye.